Welcome and good time of the day, everyone. Welcome to the online technology meetings of EPIC. And today we have a very exciting topic. We will talk about photonics for quantum industry. This topic is very vibrant and brings a lot of our EPIC members together to discuss the recent innovations and their last developments in this area. Let me remind you that EPIC is the largest photonic industry association in the world, comprising over 800 corporate partners worldwide, centered around Europe. And of course, many of them are here today, and we have a very nice agenda of speakers that will cover the topic of photonic integration for quantum technologies. We'll hear from Fraunhofer HHI today, from Fraunhofer IPMS, from PhotonFirst, from PHIX, from FEMTOPRINT, GLOphotonics, and from Diamond. This is a very nice agenda, and I'm happy to represent it to you today. So it's apart from them, we have also over 70 participants already join us online, and we will have even more of them watching our webinar later today. On this slide, you can see we have representatives of every level of the supply chain, from end user and integrators down to R&D and academic institutes. We have component modules manufacturers, equipment manufacturers, materials and service providers. All of them are here with us in the room, so I expect a very lively discussion and comments on all the aspects of how photonic integration can serve the future of quantum applications. I need to say also our meetings are supported and sponsored by several EPIC members. We have Diamond, PHIX, and Smart Act sponsoring this meeting, as well as Fraunhofer IPMS supporting us today. And in fact, before we start, I'd like to give the word of one of our sponsors, Smart Act, to say a few words about why they select this meeting to be supported.
Yes, thank you, Ivan. Good afternoon or good morning, everyone. My name is Ezedin Benamar, and I am very pleased to do a quick introduction of Smaragd today. So yeah, Smaragd is a German engineering company headquartered in Oldenburg with global customer base across photonics, semiconductors, and quantum technologies. We have full value chain under one roof with over 350 employees, separated and organized in 3 different business units, as you can see on the right. So we have first Smaragd Motion with the positioning solutions, Smaragd Metrology with the measuring technologies with our interferometer and optical encoders, and finally Smaragd Automation, which takes care of anything between semi-automated microassembly solutions, as well as fully automated complete production systems. But yeah, our core expertise lies in the nanometer precise motion for compact and highly customizable solutions, which is very important for anything in the realm of quantum photonics, because reliable positioning, optical alignment, and system stability is something that highly influences the performance there. Yeah, what makes Smaragd particularly valuable here is that we support our customers with different integration levels, so the first one being the motion components that can be integrated in already existing setups with linear stages, rotary stages, mirror mounts, and grippers. Then the second level being motion systems, so an XYZ system, a hexapod, combined with electronics and software for the reliable positioning. And finally, full solutions for specific applications such as fiber alignments, photonic chip testing, and optical assembly. And yeah, because we also have a high level of vertical integration and work in multidisciplinary teams, we can move quickly from an idea or customer requirement to working prototype. So enables us fast prototyping and allows us to adapt solutions efficiently to demanding applications. And finally, further advantages Merak offers is we design our solutions to be adapted to demanding and extreme environments, such as very low temperatures, so cryogenic temperatures at 4 Kelvin, ultra high vacuum, and also non-magnetic configurations. Thank you very much for your time, and we look forward to see how Smart can help you with your quantum photonic challenges.
Thank you, Zadine. Great pitch. Yeah, so this was a smart act in a nutshell for you. And later on, we'll also hear from other two sponsors, FEMTOPRINT and Diamond, during their technical presentations. And with this, without further delay, I'd like to start our agenda, Photonics for Quantum Industry. And the first speaker of the session will be Dominic Schulz. He's the head of business development and strategy at Fraunhofer HHI. And Dominic will talk about photonic quantum devices. Welcome, Dominic. Thanks for joining us and opening up this session.
Thank you very much.
Whenever you're ready.
Yeah, I hope you can see my presentation now.
Yeah, all good.
Good, perfect. So thank you very much for the invitation, Ivan, and also for the introduction. So my name is Dominic Schulz from Fraunhofer Heinrich Hertz Institute, Fraunhofer HHI. And today I'm going to talk about photonic quantum devices. So I structured my talk as follows. At first, I will give you a short introduction to Fraunhofer and Fraunhofer HHI. So what are our capabilities? And then I will also shed some light on the motivation, especially regarding the market projection for quantum technologies. So why are we also looking in the direction of quantum technologies? And then I will put a focus on photonic components and photonic integrated circuits, both monolithic but also hybrid photonic integrated circuits for quantum. So I will show you some examples, also let's say some of the technologies which are maybe needed. And in the end, I want to conclude my talk not by just repeating what I said, but by also bringing up some of the future challenges for quantum technologies that we as, let's say, the community, the photonics community maybe can work on, either individually or in the best case, together. So at first, let me start with a short introduction to Fraunhofer for the very unlikely event that you do not know Fraunhofer. We are the largest research organization regarding applied sciences in Europe. We are more than 75 institutes and are mainly located in Germany, but we are doing collaborations worldwide. We have more than 32,000 employees. Last year's budget was 3.6 billion. And Fraunhofer HHI is located in Berlin, as you can see here indicated on this map. And we have a budget of roughly 140 million, are more than 1,000 people, and are 80% self-financed. That's something what we are very proud of. So only 20% is really basic funding. The rest is earned by ourselves. We have three major research pillars. One is video compression and AI, so high performance video coding, and also explainable artificial intelligence, but also 5G, 6G, and photonic networks. And last but not least, photonic components and photonic integrated circuits. And this is the, let's say, area where we are going to focus on today. Fraunhofer HHI is trying to cover the entire value chain in this matter. So from the design of photonic circuits to foundry services and different material platforms, we are doing hybrid and heterogeneous integration. We do the packaging towards modules and are then also developing and providing subsystems as well as turnkey systems, which you can just use in your lab, in your rack, for example, for test and measurement, or in this case, we see an example of our quantum key distribution system. So we try to be here something like a one-stop shop for let's say all the photonic needs you have regarding quantum. Our expertise here is especially in indium phosphide, more than 40 years of designing and wafer processing. So we have our own wafer process line in-house. We are a manufacturer of wafers and chips, and we are designing and fabricating, let's say, complex photonic integrated circuits, including also active and passive integration hybridly, but also heterogeneously. And as I mentioned, we also do assembly and packaging for photonic modules. We are serving different photonic platforms or material platforms. One is indium phosphide, where we are offering also multi-project wafer runs. Thin film lithium niobate. I also put here MPW, but to be honest, it is MPW soon. So it's not yet public, but we're working on it on our PDK, and we are going to offer MPW services in thin film lithium niobate soon. Moreover, we are working with silicon nitride and also polymer. And here you can find some of the key parameters we are achieving with our, let's say, solutions. So, and all this photonic, let's say, expertise we are using for different kind of applications. And as you can see here, definitely we have our traditional markets, telecom, but nowadays we also have medical, mobility, security. So everywhere where we are going to implement also our photonic solutions. But today we are talking about quantum. So photonics for quantum industry. And I mean, quantum definitely is a topic which is, let's say, scientifically is very interesting, but also, I mean, for industry, it also needs to be, let's say, economically interesting. And this is something what we can definitely say here for the market of quantum is that we have here on the right side a graph from McKinsey. They are forecasting the market size to be growing by a factor of 10 in the next 10, or in this case now it's 9 years. So you have some significant market growth here, which makes the application of quantum very, very interesting. And also what I found very interesting, if you focus on the graph on the right side here, those kind of multicolored bars, right now it's mainly government financed, by, for example, by a research project and everything. But you will see that in the coming years, it will be reduced significantly, and you will see, let's say, what one would call real applications. So that is something which makes the market of quantum technologies very promising. What I have to mention here, those numbers you can see from 1.6 billion to 15 billion. This is only for, in that case, only for quantum communication. So if you take everything together, the numbers will be much, much higher. So in general, a very interesting market. Quantum technologies are normally divided by those 3 areas. One is quantum communication, regarding secure communication for different kind of applications, for example, in defense and security. Also quantum sensing, so using quantum effects for sensing very small signal levels and being able to sense signal levels that were not possible to detect before. And also quantum computing. I think this is maybe the most prominent, not promising, but prominent one, using quantum effects for very efficient quantum computers. On the following slides, as I said in my introduction, I will show you some examples for photonic components, also photonic integrated circuits, some technologies which may bring benefit to the area of quantum technologies. I will mainly focus on quantum communications and also quantum sensing. I brought one example with me. Regarding quantum computing, I will come to that point on my conclusion slide, when I will also talk a little bit more about the challenges for quantum technologies. So one example where photonic technology can bring benefit is, for example, for the detection of photons, of single photons. So this is an example of our indium gallium arsenide single photon avalanche diode for shortwave infrared region. So we are manufacturing those chips in-house, and we also do the packaging in-house. And the very interesting part here is that we are able to offer a component which is completely designed and fabricated in Europe, which is for, let's say, a technology which is maybe prone to dual use. Like quantum is very interesting if we can source something here from Europe. So this device will give you the opportunity to really detect single photons, which can be used for quantum communication, for example, but also for quantum sensing. Those are drop-in compatible to existing SPAT modules from Asia. So there are already some providers of those kind of devices, but not inside Europe. So this may be an interesting information. We are manufacturing those devices in 2 different versions. So in O and in C-band option, the O-band option has a little bit limited wavelength detection range, but also comes with a lower dark count rate. So next to those photonic components for quantum, I also want to mention photonic integrated circuits, which will enable reduction of cost and size regarding quantum applications. So here we are working mainly in 2 different directions, 2.5, let's say, so 2 to 3. One is a monolithic integration, which means you grow a complete photonic integrated circuits on a single die. So you have everything on a single chip, and your fabricated chip is this optical subassembly, which makes mass producibility very obvious and very easy. But you have to take all the components from the same material. In hybrid integration, you are bringing together different material platforms. Can be indium phosphide, can be gallium arsenide. So the active parts, and you bring it together with different passive parts, can be silica, can be silicon nitride or polymer, and you can even add micro-optical elements. So thereby you can bring together the best from all worlds, from all different materials, and also bring the functionality of optical elements towards the chip. But as you can imagine, I mean, the assembly of those kind of chips is more complex, let's say. So maybe gain a little bit more flexibility, but it's also more complexity regarding the assembly part. Yeah, I brought 2 examples for those photonic integrated circuits. One is a monolithic integration. The other one is a hybrid integration. You will see that on the following slides. So the first thing I brought with me is a chip a customer of ours designed. So it is a CVQKD transmitter, which was designed and fabricated on our indium phosphide MPW platform. Here you can see how many different functionalities you can find in our PDK, and you can also then bring that together on a single PIC, so you can have rather complex photonic integrated circuits on an indium phosphide chip. So here we included different active components like electro-absorption modulators, thermo-optical phase shifters, current injected phase shifters, but also we combine it with passives like waveguides, spot size converters, and MMIs. So I'm absolutely not the technical expert for this kind of chip. So if you want to see some more technical details, you will also find the publication down left here. So that will also give you an overview what really is possible, also performance-wise, using our MPW platform. So this is one way how you can really bring complex functionality on a single photon, on a single chip, for a quantum application. In this case, quantum key distributions of quantum communication. Next to this kind of monolithic approach, there's another approach, as I mentioned, is the hybrid approach, which is especially attractive, let's say, for a quantum application, because you can also bring optical elements up to the chip level. Yeah, so maybe some of you know those kind of optical benches you need for quantum experiments, for quantum setups. One intermediate step would be something like that. So that's a module which is maybe more compact, but still quite huge, quite bulky, quite costly. And the idea is really to bring everything which you see on this optical bench towards a chip level. And I'm going to show you what is possible on the next slide. So to really use the full potential of hybrid photonic integrated circuits and also micro optical elements. I took one example here. So we are using different single components. In that case, I mean, this is, let's say, the variety you can use. There are many more components you could use, and you bring that together on a platform chip, on an integration chip. In this case, it is made from polymer, and this polymer chip is manufactured in a way that we can also insert micro optical elements. So in this case, we have developed a DV-QKD BB84 transmitter PIC. So on the left side, you can see 4 lasers. Those kind are tunable lasers. So we have an indium phosphide gain chip with an external cavity here, which is made in polyboard. Thereby, you can really adjust the wavelength to the wavelength range you need. And those are then edge coupled here to the polymer chip. And here in this middle part, what you can see are, if you can see it, are let's say thin film filter or polarization controller. We can etch very thin slots into the chip down to the waveguide level, and then insert thin film elements, and can thereby achieve very high, for example, filtering ratios, or in this case, also polarization extinction ratios. So, and on the right side, you can also see that we can do this kind of fiber to chip coupling just by etching those kind of U grooves here at the end of the chip, and then directly attaching a fiber to the chip, and thereby bringing like multiple functionalities to this chip, and thereby being able to come up with this kind of polarization encoded BB84 transmitter PIC. We set that module up, and then in the end, I mean, to really make it usable, this is what we are also trying to do here, is we also do the packaging in the end. As you can see, top right here, we have the laser diodes we just saw, and here you can see some of the, in the middle of the picture, you can see some of the optical elements, and then at the end, you will find the fiber where we then can really emit the signals for the BB84 transmitter. Another example for that is a photon pair source we are developing together with a partner from Israel, which is Rykol Crystals. Again, you can see in the middle, this grayish part here is the chip. This is made from polymer. And what we are able to do is now we can etch very precisely those kind of sections here into the chip, which enables us to realize a real free space section. So on the left side here, you can see a cut through schematic of the chip. So we etch this kind of section free. We can put a Grün lens at the beginning and at the end of the section on the waveguide level, and thereby we can enable, for example, in this case, it's a collimated beam, or we could also go for something like a focus beam. And now into this free space section, we can put different micro-optical elements, which can be isolators, it can be thin film filters, polarization controllers, or in this case, we use the nonlinear crystal. So the nonlinear crystal is a PPKTP crystal, which is inserted in this free space section. In addition, we equipped, or we attached here a thin film filter. I will explain the functioning of that in a second. And at the end, we also have a polarization beam splitter to split the two photons towards different, or the two photons which have different polarization to the both fibers here. So we are pumping this laser with 785 nanometer light, and we will then emit through the spontaneous down conversion in the PPKTP crystal. We will then emit two photons at 50 nanometers, which have different polarization. They can pass the thin film filter in comparison to the pumping light. Therefore, we have this filter to really keep all the light we don't want in this crystal and not on our signal. And then the two photons are split here over this polarization beam splitters towards the two fibers. So these were examples from, let's say, quantum communication. So different sources for quantum communication, also a detector for single photons, so quantum communication. I also brought an example with me for a photonic device for quantum sensing. So what we've done here is we did the assembly for this diamond with NV centers here. If you look closely, we have here this square-shaped chip where we again etched a free space section into, and then we inserted this. You can see that here on this magnification. And then we inserted this diamond in the middle, and thereby we were able, by pumping laser through this crystal, to come up with a 3x3 array, a pixel array, which is now able to detect magnetic fields in a very, very precise way. This can be interesting for applications where you, for example, have GNSS denied environments that can be for defense and security applications, so really using the magnetic field of the Earth for navigation, or can also be used to detect, I don't know, something like in medical areas where you want to detect maybe brainwaves or something, where you're able to really detect very small signal levels and changes of the signal levels. Again, if you want to know more about that beauty here, you can check the publication I just also mentioned here down on my slide. So last but not least, I promised that I am not going to repeat everything I just said. So hopefully you saw that the photonic solutions and for photonic components and PHIX are manifold. So they're very different applications for photonics in quantum technologies. On my last slide, I also want to mention some of the, let's say, challenges we can work on as a community, as an industry, and where maybe some advancement is needed. So one is, I again separated in quantum communication, sensing, and computing. For communication, we definitely see that we have, photon loss in fibers and free space links is, let's say, critical. The development of let's say, robust technology mature quantum repeaters is needed. Also, the performance of sources and detectors can be improved. The integration with classical telecom infrastructure, there are already some experiments with that, but it's also something we have to work on. And definitely, if quantum communication is planned to be something which is more than just governmental, cost and deployment complexity has to be reduced. For quantum sensing, the same. So the, let's say, operation outside the laboratories is still something which is challenging. So the maturity here has to be increased. Also the miniaturization, if you think about those kind of sensors here, they're still quite bulky and also heavy in weight. They're also very sensitive to environmental noise, which has to be worked on. And in general, if you see this here, I mean, performance-wise, impressive, but still needs maybe some advancement regarding robustness for field deployment. And last but not least, I was not talking about quantum computing so much because there are so many people already talking about that so much. But anyways, I wanted to mention, I mean, we also see some challenges here. I mean, scalability to increase the number of qubits, definitely. Also robustness of the quantum computers to create low-loss photonic circuits, which is something that will be, let's say, a task for the photonics community to improve error correction and do that in large scale. And all in all, also the optimization of size, weight, power, and cost, which is maybe not the challenge for the next, let's say, 2 or 3 years. But if we think about, let's say, a decade or so, this is definitely something which will be, more interesting and more important. So that was my last slide. Thank you very much for your attention. As I said, hopefully you saw something which catched your attention. If you now have questions, I'm happy to answer them. And if I will not be able to answer your question, you can also just shoot me an email and contact me if you want to discuss something more in detail. So thank you very much.
Thank you, Dominic. Yes, great opening pitch. Very interesting developments done at HHI with regards to quantum photonics and integrated circuits for these applications. So indeed, after each session, we'll have a short Q&A session. So if you have a question or a comment in mind, please feel free to push this raise hand button at the bottom of your Zoom screen, and I will pass you the word. And let me just take the advantage of being the moderator here and ask you the first question, Dominic. So about this Polyboard platform, which indeed looks very exciting for applications we're discussing. So is it available commercially? And maybe just in a few words, what are the critical dimensions that can be implemented there?
So the Polyboard is something what we have, let's say, what we are working on for at least the last 20 years, I would say. That's nothing really new. The good thing with Polyboard is that we are able to really do this kind of very high precise etching. So the fiber to chip coupling is something which makes it ideally for then really low loss fiber to chip coupling and also then assembly. It is commercially available, so we are not offering it as a, let's say, as an MPW, but if you have an idea for a PIC, or if you need, I don't know, if you're manufacturer of thin film filters and you want to show it to your customers also, we are definitely open to this kind of development and also then manufacturing.
Okay, great. I see there is a question from Mirvais. Well, I hope I didn't steal your question, but please try.
Ivan, I don't think you stole it. Even then, it's shared in the community. Dominic, thank you very much for the presentation. I have a quick question, actually. If you could spend a few words on the insertion loss from the fiber in the V group, it looks very interesting.
Yeah.
Do you have any data just for the penalty, not necessarily the loss?
Yeah, so I can say the other way around. I can say something for the loss. So again, I mean, it always depends. Yeah, you know that those kind of numbers always depends a little bit on what is done. But by etching the grooves in a very precise way and also then attaching the fiber, we can go below 0.5 dB.
Okay, that looks impressive, isn't it, Mirvais?
I was muted. I actually said, wow. You didn't hear that. Wow, good job.
Thank you.
Oh, hey, can you hear me?
Yes.
Okay, awesome. So thank you. Very interesting. Honestly, I was impressed by the variety of research you guys are doing in Europe, especially Germany. So I have a couple of questions. First is on lithium niobate platform. It's very challenging to fabricate and get the high quality devices. So I'm wondering, are you guys like fabricating thin film of lithium niobates by yourself, or outsourcing those wafers from somewhere else and then fabricating devices on top of those platforms? So this is my one part question. And my second part question, you guys have amazing technology. Uh, do you guys license your technology if somebody wanna build a startup company? Like, and if yes, what are the terms and conditions? And if no, then why not?
Yeah. So for the first question is what we are doing is we are buying the thin film lithium niobate substrates, and now we are doing the processing of that. So this is what we are doing. And this is something what we also are doing for quite some years. This is, let's say, the newest material platform which joined the HHI family, but we are already doing that for dedicated wafers for our customers. So we are already manufacturing those kind of chips and PHIX for our customers. As you know, regarding MPWs, you need a stable PDK, and let's say the requirements are a little bit different. So thereby, we're still working on it. But as I said, I mean, we are trying to do that soon. Regarding licensing, Fraunhofer is in general also licensing technology. I mean, there are different ways to work together with Fraunhofer, either by direct industry research contracts, by public funded projects. And sometimes we are also doing this kind of licenses. Obviously, it always is highly dependent on what kind of technology is, what kind of numbers we're talking about. So it's not possible to really provide, let's say, a number or a cost or something like that, because one has to really look on the details here. But I mean, in general, I would say, at least I would say that Fraunhofer normally is trying to be flexible regarding the way of cooperation. Yeah. So if you have an idea or if you have anything in detail, we can talk about offline. I mean, just shoot me an email and then we can discuss that.
Okay, thank you very much, Dominic. Indeed, so the contact details of Dominic are on your screen right now. Also, if not, later on, feel free to contact me and I'll be happy to put you in touch with Dominic and with his institute. So with this, let me thank him again for the great opening speech, and I pass the word to his colleague from Fraunhofer IPMS Institute, and that will be Patrick Engelmann. He's an IC design engineer at Fraunhofer IPMS, and Patrick will talk about photonic and microelectronic technologies for quantum systems. Right, Patrick?
Yes, thank you for the introduction. So hopefully you can see my screen soon.
Yep, it's coming up right now, and then the floor will be yours.
Okay. Yeah. Thanks, Ivan and Vera, for organizing this event and also for the opportunity to speak today. As already said, I'm Patrick from the Fraunhofer IPMS, the Institute for Photonic Microsystems, based in Dresden. And I am...
Patrick?
Yeah.
Yeah. We still don't see your screen. Can you check? Do you maybe have two screens? So we're seeing the wrong one, maybe?
Okay, I will share it again. Just give me a second.
Okay, now just make it full screen and then you're good to go.
Okay, can you now see it?
Yes, now we do. Yeah, okay.
Okay, perfect. Yeah, so myself, I am mainly working on quantum sensing, but today I want to give you also The broader overview about the technologies, we are doing research at the Fraunhofer IPMS. So I will talk about photonic and microelectronic technologies for quantum systems. First, a short introduction about the Fraunhofer IPMS. So we are a research institute with over 600 employees and 4 sites, 2 in Dresden, 1 in Cottbus, and 1 in Erfurt. We have multiple clean rooms with over multiple thousand square meters of clean room space, mainly 200 millimeter wafer fabs for MEMS devices and also one for OLED on silicon for microdisplays. And our third clean room is a 300 millimeter wafer fab for micro nano electronics. And our institute is also certified for our quality management by ISO 9001. So since we are a relatively large institute, we are active in multiple quantum technologies. So we have a quantum foundry where we provide lab to fab services. And we are also active in the 3 main quantum topics: quantum computing, quantum communication, and quantum sensing. To get into a little bit more detail, so with our quantum foundry, what are we normally doing? So we are doing qubit fabrication and also integrate control and readout systems for these qubits. And we also do research and material and process development. So the value for our customers or collaborators, partners, is that we can provide industry-grade infrastructure, and we also have the long-standing expertise in these scalable 300 millimeter wafer technologies. Regarding quantum computing, our research is mainly focused on CMOS-compatible and industry-oriented manufacturing methods. Regarding the qubits and the electronic interfacing, we work on new and optimized materials, processes, and integration concepts for cryoelectronics, and also metallization concepts for superconducting materials. And we do manufacturing processes for structuring. So the value here for our customers and partners lies in the large-scale integration of quantum concepts that we can do with the silicon technologies. And we also provide an industrial standard testbed for startups, SMEs, and universities, and can provide direct link to semiconductor fabs. Regarding the quantum communication, we focus on quantum key distribution, especially for mobile applications with secure communication over short distances. We work on quantum key distribution protocols and also quantum random number generators. And we also developed beam steering systems for the use in these quantum technologies. So the value here for our customers is mainly that we provide quantum-based infrastructure networks for safety-critical data communication. Now, the last topic which I'm mainly working on is the CMOS integration of quantum sensing based on NV-diamond technology. So we are developing a CMOS backplane from industrial foundry processes to be scalable, which can then be expanded in our own clean rooms through wafer post-processing to get a complete quantum sensing unit. So we here do the full integration of all components, the light source, microwave, control, and generation, and also the photo detection and readout electronics. And this allows us to get down to very small size in the micrometer range, and also be able to potentially also create multi-channel arrays to enable multi-dimensional sensing. So the value here for our customers mainly lies in the compact and energy efficient quantum sensing module, which work at room temperature because of the NV-diamond technology. And we can also provide a very scalable and CMOS integrated technology. So now I want to get into a little bit more detail about this quantum sensing. So we are using our OLED on silicon platform here for this, the integrated quantum sensors. And why we do that, we have to go a little bit back into our history. So I'm coming from the division Microdisplays and Sensors, which is run by our head, Dr. Uwe Vogel. We are based at our location in Dresden, the heart of Silicon Saxony. So we are surrounded by all the big CMOS manufacturing fabs. And our group has mainly 2 core competences. So we are doing IC design, which is in the display part, the backplane of the display. These CMOS chips are then manufactured by commercial CMOS foundries, and then we get these wafers and process them in our own clean room with our OLED on silicon platform. And this platform we also wanted to use for quantum sensing, because our goal was to fully integrate a quantum sensing system into a CMOS chip, which means we have to integrate the optical excitation, the microwave excitation and generation, the optical detection of the fluorescence signal of the diamond, and also the control and readout circuitry. If you look at the state of the art, there has some work already been done regarding integration of quantum sensing systems, mainly the sensor head, where the optical and RF is fed externally. And there has also already been done a CMOS integration, but the main problem always is to get the optical excitation integrated, because currently that is mostly done by LED modules or lasers externally. And that is why we thought, why not use our OLED on silicon technology for this? Here you can see our proposed CMOS integrated optical quantum sensing platform, where we use the CMOS in multiple layers. So at the bottom, you have the active layer where we have our transistors and photodiodes, so transistors for control of the excitation sources. And for a readout, we have the photodiodes to collect the fluorescence signal from the diamond. Above that, in the CMOS backend, metal backend, we have the wiring to the excitation sources, but we can also integrate there the antenna and also optical matrix grading filters to filter the fluorescence signal. And above of this comes our post-processing layer, the excitation layer, where we can integrate the micro OLEDs in our thin film processes. And we are also able to integrate optical thin film filters with these processes. And on top of that comes the NVIDIA diamond, which is then excited by the microwave and by the OLED optically, and then generates a fluorescence which can be detected down inside the chip. With that, we can integrate a complete sensor system at a very small footprint in the micrometer range. We achieve a very high fill factor, and also due to the small sensor size, we have array scalability. We did multiple proof of concept experiments already, and also developed a technology demonstrator. This demonstrator, the goal for this demonstrator was mainly to do some OLED optimization regarding the excitation of the diamond, to do some also diamond optimization regarding size and density of the NV centers, and also investigate the material and technology interface between our post-process for the OLED on silicon and the NV diamond technology, because at the end, we want to have a very scalable technology that is compatible with these CMOS and OLED on silicon processes. The design is seen here. So it's a relatively large chip with 1 by roughly 7 centimeters. The size was chosen because at the end, you can see here, there are RF connectors for the RF feed. And this chip should, or we wanted this chip to be mounted in a optical test setup where we want to bring an objective relatively near to the test chip. And so that the objective not collide with the RF connectors, we made the chip relatively large. It was produced now in clean room with our CMOS compatible thin film processes. And you can see here in the middle, you have a small omega antenna. And in the middle of this omega antenna, you have the micro LED for the excitation of the diamond. To show that we are able, even with such a small light source, to excite the NV diamond, we mounted it in an optical test setup. And as you can see here, the red fluorescence of the diamond was seen with the could be seen with the bare eye, and we could also take a picture of it showing this fluorescence. So if anything from my talk was interesting to you, how can we work together? And what are we looking for? So we're always looking for partners for research projects or industry projects. So you can work with us by direct order projects, which is done mainly from industry. We are also active in publicly funded projects with industry partners or also research partners. And we are also able to provide you some solutions in a strategic partnership where we can advise you on the technical side or also develop solutions or roadmaps with you. And Fraunhofer, as was already told, is also active in licensing. So if we did some preliminary research and we have some technology you want to license for your company to bring these technologies to application, we are also always open to that. Then thank you for your attention. If there was anything interesting, you have some questions, just ask them now, or you can also reach out later to me.
Thank you very much, Patrick. Great presentation. Yeah, very exciting to see the developments at Fraunhofer IPMS. Yeah, please also feel free to raise your hands if you have a quick question. In the meantime, Patrick, so is the Institute also active in the domain of quantum computing?
Yes.
Mm-hmm.
So we are also, as I told in my talk, are active in the quantum computing area. I cannot talk about that in very much detail because I'm coming mainly from the sensing side. But if there are any questions regarding that, I would be happy to forward them to the respective person.
Mm-hmm. And maybe can you comment, since you're located in Dresden, as you say, surrounded by all the major European microelectronic fabs, can you see any traction in the interest from their side towards the quantum topics?
So yeah, especially from the quantum computing part, there are some people working with fabs, and since we are a microelectronic institute, we have active wafer exchange with fabs. Not only from fabs to us, we also exchange wafers to fabs, which is pretty unique for clean rooms from research institutes. So we are always looking to develop our technologies in a scalable way that they are compatible with foundry processes. And that is particularly easy for us because we have such good connections also to the close location to these foundries.
Okay, very interesting. Yes, and also other topics that you mentioned, like the micro displays, something that we will cover in the upcoming meetings. So we'll be glad to have your contribution there. So as long as there is no further questions for Patrick, let's thank him again for this great presentation. And I pass the word to Mirvais Yousefi, business unit manager for PIC packaging, working at PhotonFirst. Hello, Mirvais. And
hello.
Mirvais will talk about packaged PHIX for challenging applications.
Let me first of all check if I can share my slides. Yes, thank you very much, Ivan and the team for inviting.
Wait, Mirvais, we don't have the slides yet.
Yeah, I can notice that. I'm trying to share, but I think the screen is not allowing me. Here, share this. No, that's the one. All right, can you see yourself? Maybe that's the starting point. Because all right, so
that we can see.
Now it should work if all is well.
Not yet. We still see ourselves.
Okay. Oh, wow, this is fun. Let me see. I will share my full screen.
If not, do you have a blackboard? I see you have a white paper board behind you.
I can go with that. Hey, you know me by now. Let me see here. I should be sharing my full screen now. And let me go like this. And like this. And what are you seeing? My main slides or mini slides?
No, mini slides. I think if you go up with your mouse, display settings. Okay, now it's good. Just remove that little thing in the middle coming from the Zoom sub window. Yeah, this one. That's good enough. Okay, the floor is yours. Wait, now we lost your voice, Mirvais. Okay, now we still don't have your voice. So now you have to use the white paper and gestures. Exactly. So that so if you go in the Zoom window on the bottom left where you have the audio, you push the little arrow there and you can select the microphone you're using. You need to change the microphone you're using, I believe. If not, Mirvais, let's do this thing. Let me give you 10 minutes to fix these issues, and maybe we jump to the next speaker in the meantime. We have Stefan Heinemann. Stefan, could you cover up for Mirvais, please?
No.
Stefan
I can certainly do that. Let me just share my screen then.
Yeah, so Stefan represents FEMTOPRINT. He's a VP of sales and FEMTOPRINT in Enschede, Netherlands, where we had our offline EPIC meeting not so long ago. And in case you missed that one, yeah, in case you've missed that one,
right.
so Stefan,
and I
Stefan
probably
will
should
give
also.
Okay, go ahead. The floor is yours.
Cool. So thanks for the opportunity, Ivan, to present here on integrated photonics for quantum technology, and I take a different approach on manufacturing and scaling challenges. So we're not as research oriented as we had the other two speakers ahead of me, but we'll talk about if it moves forward. Yeah. So who are we? PHIX is the integrated photonics and MEMS packaging foundry. We're headquartered in the Netherlands, and I am representing the offices and the facilities in the United States. So what do? We work with all PIC platforms, whether it's silicon nitride, indium phosphide, or thin film lithium niobate. We work with about 30 different foundries to help bring PHIX technology quickly to the market. That goes from design support all the way through packaging and prototyping and packaging and high volume. Our core expertise is in hybrid PIC assembly, and we had an excellent presentation from Fraunhofer HHI on what hybrid means, so I'm not going to talk too much about this. But fiber attach, high frequencies, and electronic interfacing. So a little bit more to the details, and that's the last slide, so to speak, on what PHIX does in terms of core expertise before we come to the topic. We have four main pillars of our work in the contract manufacturing and prototyping world that we live in every day. Optical interfaces was really the starting point of the company. So low loss and reliable optic bring photons with high efficiency and reliably from fiber to chip and from chip to chip. And what that means, we're doing in high volume production, we're doing about 1 dB insertion loss in challenging applications like the quantum world. We are approaching the 100 milli-dB insertion loss. The way we do this is typically with a lot of know-how in packaging, but also know-how of optics, mode field adapters specifically, silicon nitride-based mode field adapters, lenses, and elements that allow to correct for the phase. Often, mode field mismatch is the biggest source for losses. We also have tools at our disposal for rapid prototyping, validating of the designs, specifically 2-photon lens printing. And you see one example here on the upper right, which is a freeform printed lens array of 12 by 12, so 144 beams in a coherent array. And it has lenses, as you can see, lenses, beam deflectors on the top and also at the bottom. So you have a multifunctional printed lens array. And those are very good tools for validating your approach. We also work closely with HHI actually on this project that was demonstrated with collimated beams in polymer waveguides. We use that to put isolators in, and then we write the lenses directly into the polymer board. Other expertise is micro-optical benches and flip chip integration, which is a really upcoming field of interest, where we flip chip indium phosphide into polymer or silicon nitride cavities with high positioning accuracy of less than 300 nanometers in a 3 sigma process. I also want to talk about complex system integration, because that is what quantum is about, where we have all different kinds of materials. And this is a good example of hybrid integration it's a 6T transmitter research program that really has everything from active, like the indium phosphide laser diodes, to the photodiode arrays, the TIA arrays. So we have high drive currents on one side, and then less than 0.5 millimeter away, we have very sensitive TIAs with microamps to read out. That's the kind of expertise that we have in terms of system development, system design, and then bringing that into high volume manufacturing. So optical, mechanical, electrical, and thermal design. I always say we need to bring the photons and electrons on the chip and the phonons off the chip. So we cover everything from design, supply chain, all the way to assembly. So let's go to quantum. What do we see in quantum applications? And again, I have not much additional insight to offer that Dominic didn't cover yet, but maybe just a different perspective, a more colorful perspective that you see here in terms of quantum is really a very complex field. It's a very diversified market, and Dominic gave a great overview. The main market segments of compute, sensing, and communication. What do we see in sensing specifically? Compute, we'll talk about it in a minute. Sensing is positioning, navigation, and timing, PNT, and healthcare. And you see one of those examples is actually a really interesting spin-off, a startup company out of the UK that uses the CN carbon technology that we heard about in the two preceding talks to actually measure the magnetic waves in your brain. So brain activity in a helmet type structure that can run at room temperature. The technology base for a lot of these quantum applications are atomic clocks and frequency combs that incorporate atom traps and lasers. So quantum really runs on tunable narrow linewidth lasers, but in many, many different colors. That's why you have all these colors here. You see a typical schematics of an ion trap on the upper right, where you have multiple wavelengths coming out of one peak and focusing on one volume to manipulate up to a two-dimensional array of up to 10,000 atoms at a time. So the challenges that we have in quantum, besides the market adoption, it's a super complex photonic circuitry, and we'll talk about this a little bit more as time allows. Multiple wavelengths. Wavelengths range from 370 all the way up to 1.92 microns. And then, as you can see in the ion trap, multiple wavelengths have to be superposed in one plane. So you have to not only direct the beams, but you also have to steer the beams so you can actually manipulate what's in the ion trap. And then once you have all this mastered, you have to go to extreme scalability. If you really want to have a quantum computer with reasonable qubit operation, good qubits, you have to scale to many, many 12-inch wafers at the same time. So you need very repeatable processes. And just to talk about, to better illustrate that, and we have seen pictures of complex discrete optical setups before, but this one to me is very enlightening because it really summarizes what quantum is about. You see the atomic clock at NIST in the upper right, and how it is the schematic design of atomic clock on a chip level. But the important points here are there is core components like the to lock to some frequency standards, and then you also have the vapor cells, and that is fed by lasers that cover a wavelength range from I talked about 370 to 1550. In this case, for this atomic clock, you only have 780 to 1540. But the point here is that you really need very high quality photons that have extremely high, extremely low linewidth, low noise. So they must be stable to operate over the whole operating conditions. And they must be tunable because you have to hit a very specific absorption band of your vapor cell. So very wide wavelength range, powers from microwatts to watts, and then very, very narrow linewidth, tunable linewidth. And you need those for initially. There's not a single application in quantum. It's typically you have to initialize, you have to prepare the atoms, you have to manipulate them, you have to read them out. So you have to do a couple of different operations, and that's why you need this wide variety of lasers. On top of it, I already talked about the many atoms, the two-dimensional array that you have in front of you, like up to 10,000 atoms that you would like to freeze in space and then impregnate energy levels that you need. But then you also have to move these atoms in an array form to make actual photonic operations. So you need to precise tweezers to move atoms, specific atoms out of this 2D array around. And that all has to happen in a cryo environment. Yeah, so where does photonic integration fit here? Obviously, it's super complex, and we need scalability. So let me talk a little bit about how, what we do in the field of integrated photonics. We as FEMTOPRINT execute customer designs, but I find this design a very interesting demonstration of what the capabilities nowadays are in terms of integrated lasers. And you see this in the middle here. And I don't know whether you can. No, you can't see my. But going from left to right in the upper two pictures, you see the actual gain section, which is multiple p-n junctions that are then integrated into the assembled adjacent to the actual frequency selection mechanism on a PIC. And in this case, we have 3 microring resonators in a veneer cavity that are all tunable. What it allows you is with one single gain element, you get 100+ nanometer tuning range, while you have less than 100 hertz Lorentzian line width. So this is the type of work that we need and for quantum, and we don't only need it in one wavelength, we need it in many wavelengths, and we need many of those on one PIC. One of the challenges that we see is not enough power. I mean, we need microwatts to watts, but if you have 10,000 individual beams, it quickly adds up. So we're looking also into means for scaling the power, but not with serial amplification, because that would also scale the noise, but with coherent beam combining on the chip. So how do we scale this in manufacturing? This was about the theory. How do we scale this in manufacturing? And the schematic design is shown in the upper right, where we have a gain element mounted on a submount that is hybridly attached to the PIC, which does the frequency selection. And with the frequency selection, as I showed you before, you can do many different things, from a narrow line with single wavelength tunability to a comb laser to fast modulation in the gigahertz when you heterogeneously integrated with TFLN. How does this look when it comes out of the prototyping stage into industrial applications is shown in the lower right. This is actually a light source that is not necessarily used in quantum, but it is very close to what quantum needs. It's an RGB light source, so 3 different wavelengths flip chipped onto a PIC. And the PIC does all the frequency mixing and photon manipulation. In this case, it's a red, green, and blue laser, and that is the light source for augmented reality eyeglasses with augmented reality. That is obviously these processes, to give you an idea on how quickly we put this together. The touch time is well below 1 minute for one of these devices. So this is a very scalable and scalable process, gives you high reliability. But I want to also raise a word of caution here. Testing known good die is a challenge that you need to definitely solve when you scale for manufacturing. Another example, just to show you what the breadth is of integrated photonics technology, is a wide laser source that has, that has a very wide spectrum of 900 nanometers up to 900 nanometers. And what you do here is you integrate TFLN with silicon nitride, and then you do frequency conversion on demand, so to speak, by adapting the pipeline to the specific wavelength. So if you have one pump laser, you feed that into your PIC, and then you have several sections of different thin film with a niobate to make the wavelength range of a wide wavelength range. And obviously the applications are very wide: spectroscopy, imaging, biomedical, precision agriculture. So let me summarize what we do. As we see the market, as we see quantum, quantum does not work without photonics. Photonics is the engine, if you want to say so, of what drives quantum technology. We heard that before, that there's a very strong investment from government and private equity. So in 2023, for example, the worldwide investment by federal was more than $100 billion, with about 1/3 in the US, 1/3 in Europe, and 1/3 in Asia. Private, industrial market was millions. So there's a large gap to bridge here to really bring this technology to fruitful deployment. On top of it, it's super fragmented. There's no technology basis. There's not even a technology mainstream, let alone standardization, as it is very necessary to really make this a scalable and affordable technology. The technology drivers are lasers, diode lasers, as we talked about, and ion traps. They're the basic building blocks. What do we need? PHIX with much more enhanced complex photon circuitry. And we're talking multi-layer of waveguides. We're talking wavelengths from a range of 0.5 micron to 1.5 micron. And then really also that in the low loss. So while polymers are a very interesting technology, one of the limitations of polymers might be power handling in the visible. And low loss is critical. And scalable manufacturing, I was already mentioning that a couple times. So what do we need? We need more entrepreneurs to push this technology out of the lab into real-world applications. There's a lot of private equity going into big quantum compute companies. Quantum sensing is coming up. Quantum sensing is highly defense-oriented. Let's put it this way: PNT technology is where the money is. And so that brings, its own challenges with it when it's so defense-oriented. What we also need is an extended supply chain. At this time, we have building blocks. Typically, quantum systems are very complex systems that require many PhD engineers to run. To make this rugged and in the field, they need to come in small boxes. That requires completely new supply chain. Just to mention a few, optical isolators in the visible are a pain point for everybody. Photonic integrated circuits in the visible, multi-layer waveguides, low-loss optical interconnects, and so on and so on. So there's a wide variety of gaps that need to be addressed for scalability. What we bring to the table, we are a packaging partner that is a well-known and well-reputed player in the field, and we can help companies from prototyping, early design prototyping to high volume with and we have a lot of expertise in lasers and PHIX. And I think that is the end of my presentation.
Thank you very much, Stefan. Great presentation. Thanks for also being ready to give it at any moment. Let me remind you that PHIX is also one of the sponsors of this meeting. So among with other sponsors really made this meeting available. With respect to that, Stefan, tell me why specifically this topic? Why this topic is of so much interest for PHIX?
The reason why this is we do two things, right? We do large or mid to large volume manufacturing, but we also need to feed our technology pipeline for the future. There is a surprising overlap of the AI-driven market for photonic switches, or photonic fabric is I think the regular term in quantum technology. The nice thing for us is that while the technologies are the same, requirements are a bit more relaxed in the AI world. For example, one specific example where we're looking in down to 100 millidB in photonic compute, we can easily get away with 1 dB or even higher in AI, but the technology platform is the same. So we can develop the scalable manufacturing and then optimize it with quantum. So we're looking at, today it's AI, tomorrow it's quantum. The cross technologies are very similar. The requirements are harder in quantum than in AI.
Yeah, and the photonics is the engine of quantum. I liked that quote. Okay, thanks, Stefan. I see there is a question from Rana, please.
Hey, Stefan, amazing work with the PHIX. I wish I could be in Europe and meet you in person. So I'm looking for, actually, I was talking before too. So I'm looking to build a startup, but I'm located in North America, but I want to really license a patent from Europe, because I know you guys are doing amazing work, especially in the field of photonics. So I'm wondering, because you were mentioning there, like, security challenges, etc. So let's say if there's an opportunity, if somebody can, license a patent and build a startup outside of Europe with the technology, do you guys can help us, or there is some restrictions?
And I actually have a meeting with one of your colleagues just after this one to talk exactly about that. And you may have missed it, but we're located in the United States as well. So yeah, we're definitely open to conduct business together in the United States.
Okay, cool then. I'm glad you're here.
Yeah, and I'm glad that Epic Meetings open this kind of opportunities for both of you. Okay, thanks, Stefan. Let's with this pass the word back to Mirvais. Hopefully he's over his technical problems, and now we can hear the presentation of PhotonFirst.
Yes, if all is well, now you can. And thank you very much for the flexibility, Ivan. Let me start with that. Just to speed things up and not waste more time, I will just jump in straightforward. All right, so what do we do? This is very nice, and after the last three speakers to come in, we do this, and that is an optical package, actually. That is our package. I'm holding it by the fiber. For those of us on the business, it's a big no-no, but I'm allowed to do this, and it still works. So we do rugged packaging for very challenging application, and quantum fits in the middle of this. And that's what I will try to explain during this talk. We are an SME in the Netherlands. We are actually located very close, relatively speaking, to PHIX. So we know each other very well. And we focus on initial startup to small volume, up to mid volumes, and maybe sometimes large, but normally not. We focus on that field. And our mission is to be able to take over the challenging part, that we enable your PIC to be deployed in challenging applications so that the customer can focus on the application itself, and we will take on all the challenges of preparing the PICs for these challenging applications. We're active for the PIC packaging, we're active in aerospace, in the quantum field, in defense, and in automotive, where it's mostly LiDARs. But today, my focus is purely on the quantum. And so the question, before I even jump into the quantum, the question is, why is this necessary? Why would you want this? Well, as it turns out, the PIC itself is very fragile. It needs to be nested or packaged to work in a ruggedized and real life, if I may say so. Actually, this on the right is a picture of our interrogator. We actually have our own product, a PIC-based product as a company. We're one of the only ones in the world, especially SME. The second key challenge for any PIC, this is not for quantum, is temperature control. So thermal stability is very important from the bottom up. When you design a PIC, it is a very, very narrow window of operation. We heard about resonances, we heard about frequency comb lasers. All of these require the waveguides to be in extremely good temperature control. The PICs are also analog, by the way. Most of you, I'm not sure, us in the field, we know this, of course, but not everybody realize that the PICs are actually analog by nature. So to be able to use them in our digital world, in our digital technology, we need to co-package them with electronics, and that requires PCBA integration. We heard about flip chip integration. So we don't only do flip chip PIC to PIC material, but can also do electronics to PICs. So we can do ball bonding. Finally, to get into the rough environments, not necessarily military, not necessarily space, but even in a data center, there's a meticulous documentation required for the whole journey. Your customer will require you to validate all the steps you have taken before your system enters into the data centers. And because of our 20 plus years background of building our own products, this is something we also offer the customers. We don't only take care of your PIC, we follow you through your journey. Okay, so how do we do this? What do we do? So again, here is this boy, and in the center you see its picture. So you see we have a standardized own in-house package. So we help all the way from the package design to building the package, machining this for you, validating the material, to fiber assembly, and especially fiber arrays, which is key for quantum. But then also we help to get it through the different standards, the MIL 883, for example, for microelectronics, where we take care that all the wire bonding is done correctly. And on top of that, the MIL standard, etc., we can help to increase the yield by optimizing the processes. We heard from the last speaker. And this process control will not only help you to the mid-scale, where most of our defense contract actually sits, but also for the quantum guys, we can help you to transfer this into a large-scale volume manufacturing partners. Finally, because we have our own product in the field, and anybody who has ever used a PHIX knows that it's not only the package, it's the software, it's the control, it's the TIAs, it's the board, etc. We can help with that also. We can either consult or even build this for you if you don't want to do that and just focus on your application. How do we do that? Our friends at HHI showed very nicely what they do throughout the whole value chain. We do basically similar, except our focus is purely on the PHIX, purely on the packaging and the system. So as such, we offer the design, so we can help with the thermal analysis, make sure your PHIX is feeling healthy and well throughout this life cycle. We can do the testing, and that is not only die level testing, but also, so we get the bare PHIX die from you, we can test and validate it for you, but also the fiber array units, and also the other parts, the packaging, the thermal. We can do the die bonding, of course, automated or manual, of course, wire bonding, so bread and butter, that's the standard. Then we can do fiber alignment, and you see two versions of two extremes of what we can do and anything in between. On the left is a fiber array, a multi-channel fiber array. In fact, we have done up to 128 channels for some customers. So we can do that. The PHIX material is irrelevant to us. We just need the good connectors, so the good spot size converters. For the rest, we will handle that for you. So all material is welcome, hybrid integration. The right fiber picture actually is very interesting. It's a welded fiber. A welded fiber allows me to do this to the package. Again, let me emphasize this is a real package. If you don't believe me, let me try bringing it close to the camera. And you can see it's a real package, it's not a joke. So allows us to be very rugged. At the bottom, you have our system actually on a shaker during operation for testing. So it actually works in these conditions. Now, I don't expect the database to have an earthquake, but the data center. But the data center also has some extreme conditions. I'll come back to that in almost my last slide to focus all of this towards the PHIX. Good. Well, there is my last slide. So what do we offer for quantum? So why are these challenges specific for quantums? First of all, quantum sometimes uses very exotic material. Now, even for silicon nitride and indium phosphide, there is now slowly packaging standards coming up. But for thin film lithium niobide, for example, none of this exists. So here we are very flexible. We speak to our customer from day one. We try to help them both in the PHIX design, how to get the right spot size out, how to get the right MFT, but simultaneously how to do good thermal control. And then after that, we have support them with the package and if need be in the system, as I said. The second key challenge for your quantum scenario is that it has a huge amount of IOs usually. As I said, 148 we have done. You can here see a 24-channel FAU, which we use as a demo to validate the performance so we can get ultra low loss. So those are the kind of things we can do very easily. Then your usage of the PHIX, even in a data center, requires a rugged package. Now, why is that? I mean, data center is really temperature controlled. Well, the PHIX package actually has a huge tail of fibers. Getting a mechanical stability in there, getting this to work in a consistent way and repeatable and moving it from rack to rack, moving it around, etc. That requires significant amount of know-how on the packaging where we can remove tension, etc. And we can also fan this out in a good way. Basically, when you receive a package from us, it's in a large box where everything is beautifully fanned out and you can just start using it immediately in your laboratory. Finally, let's not forget that quantum is also the champion of electronic interfaces. That's why people are going to BGAs, which is something we support. We do wire bonds up to 300, 400 per PHIX. All of this with very high quality, all the materials that are available, aluminum, gold, wedge, ball, etc. Just name it, we will do it for you. But the point is that the wire bonding, which is an old art from the 1950s, suddenly has been revived into a new handcraft because of the density of wire bonds in a photonic PHIX. It is very, very challenging to do this in a standard way, and we have methods around that. And we also help our customer at an early stage to plan their pad layouts so that we can do this. For example, we prefer just one thing I can put on the table, how to structure your grounds so that you can have a single wire bond throughout by stitching across. This is something where we ever heavily help. I'm just thinking my time. I think I'm at the right moment. So let me give you some example of where our PHIX have been. Our PHIX have been to space. So that's something where we are rugged and we know how to do this. Our PHIX have been reliability tested, as you see above, and have been on the propellers. So you can see we can handle a lot of G-forces, etc. Heck, if we continue in this way, maybe we can help Elon Musk to build those data centers in space. Let's see. Who are our key customers? Our key customers, it's a snapshot of our key customer we're working with. I'm not going to mention names, but essentially we supply and help the big players from bottom up. These are the ones I'm allowed to tell, where we do have an NDA with most customers, but only some I could tell. For the others, I'm just allowed to put logos, and that's what I'm going to do. And at this moment, hopefully you have seen all the slides. Hopefully everything worked. I'm now going to stop. Thank you very much for your attention.
Thank you, Mirvais. Great presentation and nice demo. Also in the camera, I think we'll have more and more speakers doing these kind of demos from now on. I'm actually curious about this interrogator. Is it something application specific, or can you reprogram exactly the same interrogator for space applications and all the other ones you mentioned?
Very good question, actually. So the interrogator is a fiber Bragg interrogator. So the sensors are fiber Braggs. Those can be designed for a specific application. The interrogator itself is qualified to be in space, to be downhole, etc., etc. Then we also have specific projects with customer where we take this design and we derive a specific design for them. Let me try an example. Cars. I'm not going to say which type of cars, etc., but say very fast cars cannot have the full space interrogator, but they still need the same G-forces, etc. There, we then custom package it for them, or if you want to shrink it, etc. Again, it's all based around this boy, and after this boy, we can do anything. We're actually also developing a hybrid integration, including micro benches, etc. But that's, let's say, more on the R&D level. We usually offer our customers only very high TRL 8 and up.
Mm-hmm. Yeah, well, impressive. Yeah, very nice. And when you say also welded fiber, you mean it's welded to the package or to the chip?
Yes, sir. You know what? For that, you will have to come to visit, and I'll show you the welding in live. But indeed, the fiber is welded to the package. Why is this important? Because you have no epoxy between the fiber and the lens fiber in this case, and the chip. This is very helpful in an environment where you are sensitive to outgassing, but it's also helpful very much for places like data centers. Yeah, because it operates in a certain window, but the window is rather broad, and you don't have the CTE mismatch between the glue, because sometimes you have to glue at 60 degrees to make it work at 60 degrees, etc. We can make that happen through the welding process. Mm-hmm. And we also are working, just for reference, could you say that? Something I want to advertise. We're working on fiber array welding also. We want to offer that by end of the year, which will then completely bring it to a new direction, because the fiber to chip coupling takes it on a completely different dimension, because the glue is not necessary anymore. You can start shaping the edge of the chip using these 2 photon processes that PHIX advertised to couple perfectly to a fiber array. I'll just put it on the table.
Okay.
Thank you.
Okay, great presentation and impressive set of applications, Mirvais. So for the sake of time, I will not take any questions now, but I'm happy to put you in touch with Mirvais afterwards. So let's thank him again, and we'll move to the next presentation given by Cesare Alfieri. He's a prototyping manager and business developer for Quantum at FEMTOPRINT in Switzerland. Hello, Cesare.
Hello, Ivan.
And Cesare will talk about integrated optical connectivity for glass quantum devices.
Very good. Thank you very much for the introduction. And now I'm going to share the presentation. Here we go. Do you see it?
Yes. Floor is
yours. Very good. So, thank you very much for the introduction and for the invitation to this excellent meeting. So before going straight into the topic, I want to introduce quickly FEMTOPRINT for those who do not know us. So we are a Swiss company. We are a contract manufacturer, and we are sort of small, medium enterprise. We're more than 40 people, still growing. We're based in the southern part of Switzerland, where our headquarters is. So in the small region where Switzerland speaks Italian, but we also have offices in the French-speaking part of Switzerland and salespeople in the US. So what do? We produce glass micro devices starting from glass substrates. So our technology is 3D shaping in a negative way. So we start from a glass substrate, and then we can shape whatever shape in the end, whatever dimension in the 3D with a micrometric precision. So the resolution of our process is around 1 micron, as well as the tolerance in X, Y, and in Z. So this means that customers come to us asking to realize very complex 3D objects, and we are ready to satisfy them with these performances. Also, the aspect ratio we managed to reach is very high, around 1 to 500. And we can have very straight walls with deviations of below 0.1 degrees from ideal. And in terms of the substrates we can machine, we can have a very thick chunk of glasses up to 30 millimeters, and we can machine areas up to 300 millimeters. Even if I want to be honest, the standard is more in the order of 200 millimeters, so 8-inch wafers. So here we're talking a lot about photonics and therefore about optics. And in this case, what really matters is the shape accuracy, the resolution, but also the roughness and the surface quality we managed to achieve. So I have to say that after our machining, the surface roughness is normally in the order of some hundreds of nanometers, but we are able then to post-polish the surface to retrieve the original quality of a pristine substrate, so we can manage to have roughness below 10 nanometers. So being able to shape glass with a high degree of freedom, both at the prototyping and the mass scale production level, we are very demanded for many different applications. So we work for microfluidics, for example, but also with micromechanics. We work a lot with the watch industry, with packaging, with optics and photonics, indeed. But today we want to talk also about quantum. So where does FEMTOPRINT play a role in quantum? So we produce mainly ion traps. So this, I would say, is the main device we produce for purely quantum industry. We produce also glass devices for magnetometry, like antennas. We can produce vapor cells, and we can connect these devices both electrically and optically to the rest of the world. So this is very interesting because it matches the topic of today. And that's the reason why I want to focus mainly on ion traps and how we can add photonic and optical connectivity to these devices. So these are some examples of the ion traps we can produce out of glass. So of course, our main point is the 3D. So it's not just a surface trap. We can really manage to give the designers of ion traps an additional dimension. We can produce devices that are useful for quantum computing, but also for simulations, atomic clocks, sensors, or mass spectroscopy. What is our value proposition here? So the fact is that we can really start from the beginning. So we're not scared of low volume prototyping at the beginning. So start with an idea, but then we can really follow the customer from proof of concept up to volume production. Here, volume is shaded because at the moment I haven't seen a real volume production of ion traps, but we would be ready for that. And what can we offer here? So we can have optimized the trench designs, and the trenches, for those who are not experts, are 3D features separating the electrodes. So for ion trappers, it is quite important to have insulated electrodes also after metallization and have a high density of them. So thanks to our technology, we can realize these structures that keep the insulation and the high electrode density. We can have complex 3D structures, and we can also have multi-layer traps because we are also welding glass with glass, always using our femtosecond lasers, and this allows to add an additional degree of freedom in the design of ion traps. But I also want to underline that we are heavily working and developing in the photonic connectivity market. This was originally and is nowadays mainly for datacom, driven by AI nowadays. And in this domain, we are developing mainly fiber alignment devices like V-grooves, Hall arrays for multiple fiber array units. But we can also have beam routing features, so we can write waveguides inside glass. And we can also add, thanks to the possibility of shaping glass, miniaturized micro-optics. So these are the three main building blocks, and they all benefit from the 1 micron relative positioning accuracy that we can achieve. And they can all be laser written and therefore machined simultaneously for monolithic devices. And this is very useful for optical system, for fiber to chip connectivity, and for integration into quantum devices. So just going a little bit deeper in every building block, I can show you, for example, this is an example of a fiber array unit where we can maintain a sub-micron control on the hole diameter and hole positioning. So it seems maybe not so rocket science, but it's really not trivial to have many hundreds of fiber holes that are respecting very strict tolerances at the sub-micron level and positioning. And this is quite crucial if you want to keep your losses low. So I talked also about 3D waveguides. So with a femtosecond laser focused in the glass bulk, in the volume, we can locally modify the refractive index of glass. And we create sort of a fiber in the end. It's the same refractive index difference, more or less, we can obtain in the glass. And so we have a waveguide. These waveguides at the moment are optimized for telecom wavelengths. And the reason behind that is that we need them for telecom wavelengths, as I said, for datacom. And there we have a very good positioning. We have low propagation losses in the 0.2 dB per centimeter. And the delta N, so the difference in refractive index we can induce, is not gigantic. It's in the order of 10 to the minus 2, 10 to the minus 3, and this limits a bit the bending radius. But we can have a very uniform, very nice single mode field diameters for in the order of a few microns. So here you see images for mode field diameters from 6 to 8.5 microns. We managed also to reach something below that in the very near infrared. So you have also to imagine that all this can be monolithically produced with a 3D structure around it. What we can also add are other building blocks of sort of integrated photonics, like directional couplers or multimode interferometers, and many of them are currently under development. Maybe what is not fully ready yet for the waveguides in the quantum are the wavelengths. As I said, telecom wavelengths are off the shelf now, but more interesting wavelengths, especially for ions. So I'm talking about 1760 for barium or near IR or even visible. are currently under development. So if there is someone between the audience that is interested in participating into a custom development for quantum waveguides, feel free to contact me. And finally, we also have micro-optics. So we can do refractive optical elements, for example, curved lenses, curved mirrors, but also total internal reflection mirrors and surfaces. And we can also add free-form optics. So not simply spherical lenses, but we can also have cylindrical lenses. We can have parabolic, or in the end, whatever you need. The sagittal of the lenses can be below 10 microns. And yeah, we can have multiple optical elements fabricated in a single production step. The shape deviation can be lower than 1.5 microns. So recent development also in our metrology allowed us to say that we're, for most of the cases, below 1 micron. And after several iterations that we can have with our customers guiding us also through functional tests, we can also reach below half micron of shape accuracy for our refractive optical elements. So heading to a conclusion, what we can envisage in this world are glass microconnects. So you can imagine to have a very precise hole, that's what we call a glass ferrule, that is matched with a waveguide. We can also have free propagation in glass. But let's think we need a waveguide. We can have them with very good performances in terms of propagation losses, coupling losses, and low crosstalk, even when the pitch is very small, so a few tenths of microns. And then we can have optical surfaces for mirrors, so to manipulate the beam. So in free form, in conventional shapes, this is possible with the shape accuracy I mentioned before, with surface roughnesses that can go below 10 nanometers. And all of this can be integrated within a purely quantum device like an ion trap. So this can, we believe, bring a real and solid benefit to the quantum world that we heard already many times today is struggling with packaging. So imagine to have a more compact and integrated device is for sure an advantage. And with this, I came to the conclusion of my presentation. I will be very happy to answer your questions.
Very nice presentation, Cesare. Very nice capabilities with your laser processing. I actually wonder, can several of those processes, so for example, making the glass ferrule, making the waveguide, and shaping the connector that you've just shown us, can all of that be done inside one setup with the same laser?
Yeah, exactly. So the idea behind that is really the monolithic approach. This will reduce significantly the relative misalignment between the single components. Of course, there are maybe some limitations that we discussed design by design, but in principle, yes, that is possible. So we could have a waveguide, a fiber, as I showed in the last slide, free-form optical surface integrated into an ion trap to facilitate the ion dressing, for example.
Oh, that's very impressive. Okay, Mirvais, please.
Yeah, I will have a bit more technical question instead. So I saw this very nice where you did directed the light down. The question, because you had the very nice slot for the fiber also. This requires both etching and writing. Do you do that together in one process? I think I want to follow up on Ivan's question. So, or do you separate?
Yeah. So I didn't want to go too much into the detail for a lack of time of our process, but our process is a two-step process. So we start with a laser writing. We start from a glass substrate and we focus the femtosecond laser inside the volume. This is like a spot, a pen that defines the shape. By defining the shape, we induce selectivity against a wet etching solution. And the second step is we put the glass into the etching. So the laser is not removing any material, it's the chemical etching that is removing the material. So it's a two-step process, but all the features are then written and etched together. And this preserves the alignment and accuracy.
Okay, I was just going to compliment on that, but good you say that. Thanks.
Okay, if there's no further questions, let's thank Cesare for an impressive presentation again. And we move to the next speaker, Thomas Billotte. He is a quantum engineer representing GLOphotonics. Hello, Thomas. And Thomas will talk about fibered gas cell for quantum applications.
Okay, everyone can see the screen?
Yes, the floor is yours.
Okay, fine. So hello everyone, I'm Thomas Billotte. I'm working in GLOphotonics company in the Quantum Tech Business and Technology unit. And I'm going to present you today fiber gas cell for quantum applications. So GLOphotonics is a deep tech company based in France, and we are developing photonic components based on hollow core fiber technology that we are designing and fabricating by ourselves. As you can see, there is different design, and we can address different guiding wavelengths, different core size depending on the applications, and also different modal content, because we'll see later that sometimes single mode is not the target of the applications. And we are doing post-process on this fiber to create what we call photonic microcell to address different applications like beam delivery, pulse compression, and quantum technology. So I will divide my speech in three parts. First, GLOphotonics capabilities on hollow core fiber and post-process. Then photonic microcell as fiber gas cell and an example of magnetometer based on this technology. So as I said, we are designing and fabricating hollow core fiber with our own fiber drawing tower. As you can see, we are doing the preform, we are drawing the fiber and obtain, as you can see on the left, what we call Kagome lattice, and the light is guided in the hollow core. We are performing post-process on this fiber, like glass post-process, microlensing, engraving, splicing. And also we are filling with fiber with gas to create what we call photonic microcell, which is basically a hollow core fiber filled with a gas. And at each end we have a termination, could be optomechanical, or could be fiber one. And fiber one is the one we are using mostly in our quantum technology units. So photonic microcell, the aim is to address different applications like geophysics, space, GNSS, and basically quantum sensing, because as you may know, a good quantum sensor is set by how good its associated clock. And today's best clock performance measured in fractional frequency instability should be around, are around 10⁻⁹, which is a crazy performance. But for many applications, 10⁻⁻13 could be sufficient in the condition that the device is compact, integrable, low cost, low size, and so on. And this is where hollow core fiber and PMC technology are a key enabling technology for miniaturized atomic clock and an alternative to printed chip, as we've seen during this presentation, during this meeting. So this is a panel of molecules that we can use to create atomic clock. And there is two, iodine and acetylene, we choose to fill the fiber with. Iodine for visible wavelengths and acetylene for optical communication wavelengths. So what we are proposing is a hollow core fiber with low loss, sealed at each end with the gas sealed inside. And if we compare the performance in terms of absorption contrast with a standard gas cell, by standard I mean the bulk gas cell that we can find on different supplier, we can see here that the contrast is like 7 times higher compared to glass cell at ambient temperature, which is interesting because the performance of the clock will depend on the signal-to-noise ratio and the line width of the peak. And then we perform some what we call Doppler-free spectroscopy to obtain very narrow signal, as you can see here in blue, based on this hollow core fiber technology. And at the end, we are stabilizing some laser with that to obtain this fractional frequency instability. And the result here obtained by some collaborator with our PMC reached close to 3×10⁻13 at 1,000 seconds, which is consistent with what I exposed before. So for iodine PMC, advantage of this technology is very high contrast at room temperature and the integration that you can have because it's fiber. And for iodine, you can cover wavelengths from 500 to 700 nanometers. Now I will switch to acetylene. So it's the same kind of device, it's just the gas inside that is different. So of course the process of fabrication is different because iodine and acetylene does not have the same reactivity, chemical reactivity, and so on. But here what we observe in terms of spectroscopy, we can see here the Doppler-free signal, the small transparency peak in the middle. It's quite clear for acetylene, and also we measured the stability line width of this signal, which is stable after years. And same then for iodine, we stabilize some laser, and we are here at 10⁻11 fractional frequency instability. So for acetylene, what we have low insertion loss, very high contrast also, long lifetime, and this one addresses basically telecom wavelengths. Other advantage of this PMC is because the hollow core is about tens of micrometer diameter. You don't need so much light, so much intensity, so much power, sorry, to saturate the transition to obtain this peak. So because the intensity is quite high even with lower power. So now we'll switch to the example based on this PMC technology, which is integrated optically pumped magnetometer. So what is it? Let's imagine you have a group of atoms, let's say the rubidium atoms, and you send some laser beam, you will orientate it, you will have some spectroscopy signal. And now if you apply a magnetic field, the orientation may change and the absorption of the spectroscopy may change also. And this is how we can measure some magnetic field intensity. Now let's imagine that we do not have a Gaussian beam, but let's say kind of donut-shaped beam, Laguerre Gaussian beams. Here in this case, each part of the beam will be affected differently by the magnetic field. The atoms inside this beam area will be affected differently. And so we will not only detect the intensity of the magnetic field, but also its orientation. And this is the theme, the issue of the VMAT project. It's a collaborative project with different partners in Europe. And the idea is to create an optically pumped magnetometer. So exploring, of course, theory, experimentally in standard gas cell, and creation of this magnetometer in a fiber way. So our part of this project is to create a PMC filled with rubidium to address this topic. The rubidium is a very specific atoms, like all the alkali, because they are very reactive in a chemical point of view. And to handle it, you need to process at very low, or sorry, very high vacuum, like 10⁻7 millibar, something like that. And due to this, it's very, very long to load the fiber with these atoms. It could take more than months. And to address the sealing and to address all the parameters that we need to really encapsulate this rubidium inside the fiber, it's too long for us. So what we choose is to use, as a first step, to use capillary, slightly larger. This is the object of a presentation, is SPIEE Photonic Europe recently. So we fill some capillary with rubidium, which is much, much faster, approximately a week. So then we can study the loading dynamics, the splicing parameter for different material, because we can use silica, which is basically the material of the fiber. Borosilicate could be also some useful for encapsulation or things like that. And also some coating. This one is called OTS for anti-relaxation properties. And we successfully sealed rubidium inside. We can observe here, we have a connector. It's not really plug and play, but we just can connect some standard patch cord and observe some absorption signal at the output. And these ones are stable now after more than a year, close to 2 years. And we are trying to perform, of course, some Doppler-free spectroscopy in these devices. And we continue to develop this capillary because it's not only a step, but it's also a device itself that could be used for some applications. So to conclude, what GLOphotonics can offer, we can offer on-demand hollow core fiber with different core size, modal contents, because as you have seen, sometimes we need not Gaussian mode, but higher order mode, and different guiding wavelengths to fit your applications. We can also fabricate PMC with gas inside, with acetylene, iodine, carbon dioxide. And if you need something different, you can also contact us. And we can also open to collaborative projects or custom engineering to develop your fiber solution. And what we're looking for is some collaborator to be final user or characterize this kind of PMC, for example, iodine, to have more and more feedback to improve these products, and of course to diffuse the hollow core fiber technology, because probably in some years is the fiber that will replace the standard fiber we have today, for example, for communication and so on. Thank you for your attention, and if you have questions, I'd be happy to answer.
Thank you, Thomas. Great presentation and great capabilities of photonics, of GLOphotonics. It's, I think, a very unique company operating in Europe, in the middle of France, actually. And yeah, I mean, you've spoken mostly about the quantum sensing, but of course, quantum communication and also quantum computing could be a topic. Can you say a few words about those developments, maybe?
For quantum communications and quantum computing, we are not working so much there, but it could be used, of course, since we can place some atoms inside and we can cool them and so on. You can create some qubits and you can address this different topic. To be honest, we have not started yet to work on this different topic because, yeah, we are a small team, 15 people, not working all on quantum technology. But of course, if people are interested, we would be happy to collaborate and on some project to this topic, of course.
Yeah. I think I can find some collaborators for you for this topic. That's really raising right now. I can see that. Any other questions for GLOphotonics? If not, I suggest, you reach out to me or to Thomas afterwards, because we really need to catch up on timing now. So let's thank Thomas again for the very nice presentation. And we switch to the last speaker of our session today, Régis Blin. He's a sales engineer working in Diamond, a Swiss company represented here. And Régis will talk about redefining low-loss fiber optic interconnects.
Yes, thank you. Thanks, Ivan, for your introduction. So, okay, can you see my screen?
Yes, we do. We don't see the presentation though. We see the Zoom screen.
Okay. Let's go back to Zoom. Okay. Share the window. Okay. So, do you see it now?
Yes, now all good.
Okay. So thanks for your introduction. I will try to catch up with the time to go to the point. And Diamond is a Swiss company, so we we manufacture high precision fiber optic connectors and assemblies. And Diamond is manufacturing since over 20 years low loss fiber optic interconnects. And then low loss means our standard 0.1 dB class. It's an insertion loss below 0.15 dB. And we have been challenged by the industry, particularly quantum industry, to improve that and to try to deliver a product with repeatable performance and with a lower insertion loss. And so here I speak to fiber connection. And so we came lately with a ultra low loss connector, ultra low loss with insertion loss max 0.04 dB. So that's our new class of connectors. So that we could achieve with improvement in our manufacturing process. And so that's in the next slide, I will share a bit how we can achieve such performance and what we can deliver to the quantum community. So a look in the past on how we could progress over the years from since Diamond is manufacturing high precision fiber optic connectors and invented E2000 connectors in '92. So it's a grade B standard telecom connectors, insertion loss max 0.25 dB. And looking at what is relevant, instead of speaking of only in dB, it's to look at the transmission. So which progress we could do over the years. And that now we are reaching transmission with a ULL class, ultra low loss, up to 99.5% with fiber-to-fiber connections. So that's it's really new, and we are consolidating our manufacturing process now. And what we could improve, I mean, in terms of what we have to solve to reach such low insertion loss is first the geometrical parameters are fiber, so fiber and mode fit diameter mismatch. So this is so it's purely depends on the applications, and taking into account that we use the same fibers, what we need to take care about is lateral misalignment and angular misalignment. And the biggest contribution to losses is lateral misalignment. And here I don't mention obviously the surface, so polishing and cleanliness of the connectors that need to be top quality. And considering lateral misalignment, how we can work to improve this, to get the best performance. So let's see the fiber. So we work with commercial fibers. So there is nothing we can do. What we can improve and what we have under control here in the factory is at the ferrule level. We manufacture our ferrule, so we have control on the ferrule bore eccentricity, and the final assembly of the fiber inside the ferrule. What we do with the so-called active core alignment is that we have a control on the position of the fiber. So we do alignment on the fiber, not on the ferrule. So, and we correct this lateral misalignment to the sub-micrometer range. So first, so what we need to do such alignment is our two-component ferrule. So it's a famous titanium insert with ceramic sleeve with a high precision ferrule for a perfect matching with a sleeve of the mating adapter. And then alignment, so active core alignment. What we apply is that, as you can see, I see what you can see here is titanium, so it's a ductile component. We apply an arc shape crimp, and that enables us to correct eccentricity to below the micrometer. And how it works, so there you have the titanium ferrule, so it's a typical video. So we check eccentricity and then apply the crimp. So here it's we have this individual ferrule, and it's encapsulated in this example in an E2000 PC ultra low loss connector. Here it's a check, so you see the wedge shape on the titanium insert, and then the connections, the mating, to reach 0.017 dB. So this is a 99.5% transmission. And the big advantage of this process is that it's independent from the fiber diameter, and so I have to show you some performance of these improvements that we latest introduced. So it's an improvement in terms of image processing of our process of our tool to produce this active core alignment in the production line. Ultra low loss, it's difficult to measure. It can be a lot of uncertainty in the measurement because we are really close to the noise level of detectors. So what we did at qualification is to random mating. So one connector is mated to all the other connectors of the set. So here it's 20 patch cords, 40 connectors, and 1,500 connections. So it's a lot of work, to be processed carefully. And 97% of the value is below 0.04 dB. And this distribution is a Rayleigh distribution of the losses. So it's this displays our measurements. NIST has compared this measurement, so they get a really good correlation, and they will publish their results this year in the next conference. It's a GLOphotonics conference. So, and 1550 is a core diameter 9 micrometer. Let's go to 780, so smaller core, more difficult to correct eccentricity. And then here it's 97% of the losses of the connections have losses below 0.08 dB. And also this is a part of the cross-check done by NIST with a perfect match with between our measurement displayed here and their measurement that will be in their paper. And so now we go to production, to volume production of this ultra low loss connectors. So random mating is not practical. It's not sustainable to do that for any kind of industrial production. So what we need to do is we focus on the controlling every kind of individual parameters of our production. So here at Heinemann, we have vertical integrations. We do our own ferrule. We manufacture everything from the ceramic to the mechanics to the plastics of the body of the connectors. So this enables us to get this really good performances and these expectations that we have with ultra low loss. It's the curve that I show here, from visible to infrared, with average losses down to 0.15. Yes, I hope you see my screen because I have a message. I have this. Can I move this? Yes. Okay. To at 400 nanometer. So we have here a combination of measured performances and simulated performances, and we see this good correlations. And consider that going to ultraviolet, so single mode, the mode field diameter gets smaller, so it's even more difficult to align. So we measure this insertion loss now in production against reference. So this eliminate outliers. And doing that, we have the perfect control of our manufacturing process. So we remind you at this relay distribution that I displayed earlier, and we cut some outliers that are in the production batch with insertion loss against reference. And yes, what we can provide to the quantum community is to have a connector, so the flexibility of the connector with the performance of fusion splice. Ultra low loss, a short indication of configuration of these connectors. So we started this with a NIST, it's E2000 connector, and now we have introduced FC connectors, mini AVIM. It's a connector withstanding high vibrations, and DMI connector. DMI is this one. It's a ferrule kind of connector. So we provide standard components as well as custom assemblies. And here's some example of matrix connectors, optical phase through. And we work on single mode polarization maintaining on photonic crystal fiber with wavelengths typically from ultraviolet to infrared. So a few words on Diamond. So we have 220 employees in Switzerland. Engineering production are here. So vertical integration means we have a lot of flexibility to make a customized solution, because ultra low loss is a technology that can apply to any kind of fibers. Some are qualified, as I showed here in the slides, from 1550 and 780, and other capabilities we still discovering new performances, and we do small production batches test for any kind of request that we can have. So we have also clean room assemblies capabilities for really complex assemblies and requiring down to ISO 5 clean room. So for I think I am finalized with the time. If you have any questions, you can ask me now or take my contacts information, and we'll be pleased to have a further detailed discussions.
Thank you, Régis. Great presentation. Yeah, and very interesting to see your indeed powerful capabilities and the vertical integration of Diamond. Mirvais, please go ahead with your question.
The usual suspect, I suppose. Hey, Régis, thank you very much for a nice talk. Can you spend a few words of PMF using this technique? Because I assume it's a slightly different challenge than let's say round core SMFs. So what happens when we want to have polarization maintained?
Polarization. So you need you need a control on the orientation. So our standard orientation is on the slow axis. So we take in consideration that for ultra low loss, we focus on this product family on insertion loss. So our goal is to provide lower losses, keeping the same polarization expansion ratio performance of our standard polarization maintaining fibers. So that's we need to know what is your priority. So we provide building blocks for photonics integrators. So if your priority is on polarization extension, we can push on this side. We have PM plus fibers. And if you need to push on insertion loss, we have a low loss that we do since 20 years on ultra low loss. So you need to find a compromise, because both impossible.
If I may, I think let me extend on this, because the quantum applications, 99%, at least on PHIX, are extremely polarization sensitive. So PMF is a key to success. So my question would be, because looking for our customers here, could we, instead of FCAPC, use your connectors? And could you then guarantee the same insertion loss performance using a PMF scenario? So maintaining polarization during the coupling.
The performance displayed in this presentation are for single mode with a E2000, so connector polished at 0 degree. So when you add the orientation requirements for polarization maintaining, you decrease a little bit the insertion loss in comparison to the top performance that we can get and that we work on with the NIST. And that considers that in comparison to our standard PM fiber, we can improve by 50% insertion losses with this technology. So that's, let's send us your requirements and we can work on the simulation to provide you some targets.
Perfect. Perfect. That's the spirit. Maybe to conclude this meeting, I'll also ask you another question, Régis. Is there something where our community can help you with in your developments? Something that Diamond can benefit from having this epic network around you?
What we can benefit from fiber manufacturers, because the fiber is the only component from our assembly that we don't manufacture, and also what we need to know is different applications, because as you see, we have tested mainly at 780 and 1550 for now, and we did other small qualification on smaller batches on other wavelengths. So as it's quantum is a really fragmented market, we got a lot of requests from different configurations. And that I think from the communities to explain us, to ask us what is needed, so that we can focus our efforts on that one.
Okay, that's clear. Okay, well, thank you very much then with presenting Diamond for us, and also thank you for sponsoring this meeting, for making this whole thing possible. And with this, let me close this technical part. Let me just say a few words in conclusion. So this was the online technology meeting of EPIC on photonics for quantum industry for you. Right now you have this feedback poll on your screen, so please give us the feedback of an overall rating of your meeting and something where we could improve. Would really thank your feedback for us. And I would like to thank again also all the speakers of this session. So Dominic, Patrick, Mirvais, Stefan, Cesare, Thomas, and Régis. Thanks again for your time and for sharing your insights on the quantum industry. I will also say that EPIC is there for you to help you with technology expertise, with providing market studies and opportunities in networking and mentorship, recruitment and investment. And I also thank my whole team of EPIC for making this meeting possible, as well as again our sponsors, Diamond, PHIX, Smart and Fraunhofer IPMS. And with this, I'd like to thank also all of you for your attention, and I see you on the next occasion. Thank you.
Thank you. Goodbye.
Thank you.
Thank you, Mirvais. Thanks, everyone.
Thank you very much.